No takers? Okay. What we tried working with last time was the basic notion of what a manifold is. Can everyone hear me?
Yeah.
Okay. So I tried arguing to you that if we're looking to describe physics in a curved spacetime, the notion of curvature does not come free to us. It's not a free construct. It needs to be developed. And I argued to you last time that the mathematical construct that allows you to discuss curvature or discuss continuity is something known as the differentiable manifold. That's something that was the biggest idea of last time's talk. Okay, so we started off by saying that our starting point for GR is something that you can think about as a canvas. It's like a canvas, it's called a manifold. Okay, and a manifold is a structure. It's something that's added onto your set of real numbers. It's structure that's added on, which ensures that you have continuity, and you can talk about smooth curves, differentiation, calculus. All of that needs a manifold to begin. Okay, so manifolds tell us about continuity. And the idea of continuity is that if you have a bird in the sky, if it's moving from one point to another point, it won't magically disappear and reappear at another point in the sky. It traces a continuous path from point A to point B. Okay, we don't know what that path is yet. We're not making any predictions. The only thing we've said so far is that she needs something called a manifold. And underneath this discussion of a manifold, the second biggest idea was something called a locally Euclidean space. Do you remember that? The idea was that when you work with gravity and GR, in general, these manifolds could be extremely ugly and they could look very complicated. So our work to simplify this was a very elegant idea that says that if our manifold is a circle to begin with, we're going to picture ourselves as being ants standing on top of this circle. Which is to say that if you were an ant standing and you only looked what's around you, just like the Earth is a sphere but looks around us like a flat plane, if you were an ant on the circle, the spaces around you would look more or less flat. Does everyone remember? This was the notion of a locally Euclidean tangent space. Right? That's what we spoke about. That with every point that you have in its neighborhood, and we used topology to something where any point in this manifold, you can take a point, you can look at its neighborhood, and we use the terminology that was called isomorphic, meaning the same form. And isomorphic means that in the real world manifold, if you have any point, you look at the neighborhood of that point, this neighborhood for all intents and purposes is the same as flat space. Or in our case, in GR, we're going to say it's Minkowski. Okay, that was the second biggest idea. Is everyone on board? Do you remember? This was fairly mathematical last time. I introduced concepts from differential geometry. We looked at things called maps. And we looked at inverse maps. Do you remember?
Yeah.
These were, we said, whatever you're at in the real world, whether it's your bedroom, for example, the bedroom in your real world, whenever you do physics, you're never touching the real world. Okay, whenever we do physics, we're looking at a representation of the real world in your locally Euclidean or Minkowski space. Which is to say that so if you were to chart and draw your bed in your bedroom, this is the world that we do physics in. And if you wanted to correlate that to the real world, you have to take the inverse map and go back to the manifold. So whatever point you have here, the inverse map at that point corresponds to the real world that we work with. Okay, do you remember that? That was the second biggest concept that we spoke about, that globally the world is curved, but locally we can describe it by flat space, and flat space is nice because we can apply what we learned from special relativity. Okay, so we spoke about locally flat. Okay, the last thing that we ended the lecture with was an introduction to the metric tensor for the first time. And if you remember from special relativity, the tensor that we worked with was this quantity we called eta mu nu, right? Which was we've all drawn this a million times now. It was this matrix or a linear transformation that looks like this, which allows us to convert row vectors to column and column back to row. Or in the language of physics, it's converting from contravariant to covariant and vice versa, right? We said, however, that in general relativity, this metric changes. So the argument we spoke about last time was that if we had a weird manifold that could look strange like this, right? We're only going to be working at a point, and in that local point, wherever we are, it looks like Minkowski space. But the idea that what we said is that at every point in our manifold, we will assign a metric at that point. So to every point, there will be what's called a metric. And the condition for special relativity was that wherever you are, for every x that you have in your manifold, g mu nu of x is eta mu nu. Does everyone see what this argument says mathematically? It says that for every point in my manifold, the metric tensor of general relativity is in fact the tensor of special relativity. So this is the defining condition of special relativity, as it were. But for GR, this is no longer true. So for every point x within your manifold, you're going to have some tensor associated with it called the metric tensor, which we'll see today helps us talk about distances. But this no longer will be that familiar form of -1, 0, 0, 0. It could be fairly complicated. And we can see a few examples for this in time. Now, if we're learning GR, I was wondering whether all of you who were part of this were thinking, why are we learning about manifolds? Why are we learning about different things? So I thought I'd show you just a brief outline of where you'd want to go with the course in GR. And so if you were to look at Einstein's equations, okay? Einstein's equations, if you remember you may have heard from popular science or whatever, that on the left-hand side you have space-time. And Einstein's equations say that space or whatever is the same as mass and energy on the right-hand side, right? You would have seen some sort of equivalence like this in popular science, right? Our goal is to build these concepts mathematically, and the construct that has all the information about space-time in it is something called the Riemann Tensor. Okay, it's this object here. We don't know what that is. We haven't got around to defining it yet. Okay, so all the information about space and time is codified in here. And we're going to take this huge, big tensor, as it were, and we're going to look at a small subspace within it. And that small subspace is what's called the Einstein Tensor. Okay, it's just this. And on the right-hand side, the tensor that we're going to be learning about, which codifies and has all the information that we need about the mass, how much mass is concentrated in a point, or a volume element. All of that information is given in terms of something that's called the stress energy tensor. And that stress energy tensor is labeled by T. And of course, as you know, from the left and right side, we should have the same number of equations. So it turns out Einstein's equations aren't one equation, but we learned that there are 16 equations, which if you use symmetry constraints, we bring it down to 10. And on the left-hand side, we have something which relates space-time to something which relates mass and energy. So our goal at the end of the day is to try and understand what these concepts are. Because if we learn these, it'll help us understand what Einstein's equations are. And once we know what Einstein's equations are, we'd look for solutions of these equations. And that's where we get to what everyone wants to be studying about, black holes, right? But the reason that I'm hesitant to go to black holes immediately is because if I write down the line element, what the g mu nu of a black hole looks like, you're not going to understand anything about it. It's not useful to you yet because guess what? When you do differentiation and calculus on curved manifolds, the physics changes completely. We can't simply naively apply what we've learned earlier to a curved space-time, which is why it's a lot more complicated than what we're used to. and we have to pay careful attention to how we do that. So the goal that we're trying to do is to first understand what tensors are. And for us to understand what tensors are is what we've started doing so far. We've ticked off understanding what a manifold is. Right? We know what that is. We've spoken about tangent spaces last time. Do you remember that? Tangent spaces. And we began with the definition of what a metric is. And if you remember the equation I left you with last time, I said G mu nu, the quantity that I call the metric, is defined as a dot product between two different basis vectors. Do you remember this? This was the equation where I left off with last time.
Yeah.
Okay. And what you're going to see over the course of this, hopefully this week, at the end of it, you'll be seeing examples. This quantity here, okay, that you see here, is made up of the derivatives, it's a function of our metric tensor. It's also made up of the derivatives of our metric tensor. So we're just going to take, this is our starting point. And from our metric tensor, we're going to build and build and build until we arrive at this quantity on the left hand. And once you've understood what this is and how you play around with the metric tensor, that's doing GR. And you can start to, on your own, go out and look for interesting problems. Because the moment you understand this framework that we're going to be doing today, you can apply Einstein's equations to study any field in astrophysics, whether that's dark matter. Remember, dark matter is a relativistic, it's a non-relativistic phenomenon, but you have to describe it using gravity. So it comes into play here. The second is in cosmology. Anything that you're doing in cosmology is a solution to Einstein's equations. So it's useful to understand that as well. The third is to go into black holes. Okay, I think I see notifications in the chat. Okay, Bhargava, just give me a shout if there's a question that I missed out. If you guys have just come in here and shout. Okay. So if you remember last time, where I left you off was to say that in our manifold, right, we have something called a basis vector. And do you remember what that basis vector was? We said that if you have a curve that's in our manifold, okay, you have a curve. Whenever we talk about the curve, remember now that we'll only be talking about the curve in our notebooks, which is to say we have some map here, and we have a representation of that curve in our notebook. And if we want to know what the real world curve is like, we'd have to take the inverse map of this. Okay, and anytime we do physics in terms of describing a coordinate system of any kind, we're not really touching this. Okay, remember, we're not touching this. What we're doing, in fact, when we build a coordinate system is forming grids here, in our world here. Okay, and what that means is that if you ever change your coordinates or you look at it from a different perspective, polar coordinates, whatever is useful to that particular calculation, you're not changing the real world. You're only taking a different map of your notebook. And you'll now describe that same thing in terms of various other coordinates. Okay, so do you remember that? And the point of this is to say that what we want to be building today is, I just want to revise what I spoke to you about with tangent space. And if you remember what I said was that at every point in our manifold, right, at every point in our manifold, we have something called a tangent space. And the crucial thing to note is that no two tangent spaces are the same. So this thing and this thing is not the same because locally they are flat around that point, but we can't correlate the two of them. And that is the problem that we need to address today. The problem, which is that if we wanted to do integration or we wanted to compare vectors, for example, right? We take a vector that's pointing here, we take a vector that's pointing here, and we say, well, if we have two vectors like that, the resultant vector is like this, right? We can't really compare vectors, we can't talk about lengths, because it turns out that one vector that's in this space isn't related in any way to the vector that's in this space. So it's a little difficult for us to compare between these two because they live in two different spaces. So it would be a big error if we just said, well, the tangent spaces at every point are the same. If the tangent spaces at every point was the same, you'd have Minkowski space. Okay, so before we begin today, I thought I'd quickly give you two definitions of what are tangent vectors. Okay, so if you remember last time, the first definition of a tangent vector is I called it this quantity t. Okay, so this is the notation for what a tangent vector is. So if you can see, there are three letters. T stands for tangent, M stands for the manifold, P is at the point P. So that's everything that all the information that is spoken about here. That at each and every individual unique point P in our manifold M, you don't see the T. Can you see it now? Well, yeah, it'd be easier if you talk because I have to pause and go back to the.
Okay, now I see the T. Okay, right.
Okay, so essentially, this is just notation. It's notation that says this is my tangent, M is my manifold, and P is the point. Okay, and if you remember last time, we defined it almost like this operator, which was that you're going to take the differential of your function at a point. Do you remember this? The example we'd used last time was something like if I have a function like y minus x squared, you'll have to find the tangent vectors of this. It wasn't y and x. I think it was lambda squared. Do you remember this? And to find the tangent vector, you just have to apply the differential operator. Yeah, that's what we did last time. Does everyone remember? And we said, well, the definition of this is then we've set. Remember, I'd given you two examples. One where lambda was 0, the other where lambda is 1. Do you remember? Do you want me to revise this again? Because I wanted to discuss an alternative definition of a tangent vector today. And a tangent vector is that it's the directional derivative of a function, okay, along a particular, which is to say that a tangent. Can everyone see that?
Yes.
Yes, it's visible. Yes.
Okay, so this is an alternative definition. We're talking about the same tangent vector that we've spoken about so far, which is in my drawing, it's this thing. Right? It's the same vector. I'm just going to give it another definition, which might make no sense given what we've been speaking about. And all I'm going to say is that it's this quantity. It's the directional derivative. Okay. Oh, sorry, I don't have my coordinate system. Yeah, it's the directional derivative depending on your parameter. If my curve is parameterized, last week we used lambda and said our curve is just parameterized by lambda, which is to say that x of lambda is this curve. So at lambda is equal to 1, I have this particular point in my curve, which is characterized by 4 points, x0, x1, x2, x3. And at lambda is equal to some other value. Maybe this is lambda is equal to 1, lambda is equal to 2. I get back a different set of 4 coordinates, which describe my curve, right? So if we're running with lambda, I think lambdas were used last time, right? This is our directional derivative of our curve, of our function along a curve. Okay, and I'm going to set lambda equals 0. And this is an alternative definition of my tangent vector, and I wanted to show you something interesting with this. So can you all see so far that I don't have any coordinate system here? It's independent of my coordinate system. Can everyone see that? I don't have an x, I don't have a y, I've not chosen radial, polar coordinates, nothing. So far, it's an abstract function that's essentially a curve on my manifold. And I'm asking what's the directional derivative along a curve. If you want a physical interpretation of what I've spoken about here, it's the idea of you go outside running. You just run outside and you report back what changes you see with the weather around you as you run. Like if you're running in Besanagar, the closer you get to the beach, it might get more humid. So you pick a function. This could be humidity, for example. F could be humidity. And what you're doing is you're changing your function along a particular curve. So you're going to run around Besanagar in a in a particular path, and you're just going to report back to me how is the humidity changed while you were running. That's all this describes. That's a directional derivative. We're taking a derivative of a particular function in a particular path, which is, it's just measuring how the function changes along this particular curve. Okay, is everyone clear so far? So now note something that we can do. Okay, in general relativity, we want to start with the definition that's independent of any coordinate system. And to do calculations of any kind, we insert a coordinate system. Okay, and there's a really nice way of inserting coordinates, which is almost like using an identity. You guys have probably, in various areas of physics, you would have multiplied something by 1, right? And rewritten that 1 in a clever way. Have you all done this trick in many different places? Like, I think in linear algebra, for example, you might have A, like a matrix A, and you might take 1 and write 1 as B and B inverse, right? Have you all used this trick before? Is this a new trick to anyone? I need
Yeah,
some
we do that.
feedback.
We do that a lot.
Yeah. Okay, so the point of inserting coordinates is the same as inserting the identity. And what we're going to do is insert coordinates here in the following way. We're going to take our function and write it like this. Can everyone see what I've done? I've essentially taken the same function that I have up here, and I've inserted the identity. And anytime we insert the identity, this is inserting our coordinate chart or a choice of coordinates. What I've done is I've chosen x mu. And I've just asked how f changes with x mu, and then how x mu changes with t. So it's almost like I think it's called the chain rule. But this is what we've done. We've involved and inserted our coordinates here. Okay, and once we do this, I wanted to show you that there's a particularly interesting way of writing down what this equation really is, right? And if I take out f from this, can you see this thing is actually just, it's actually not t, sorry, it should be lambda. Yeah, so this thing is, sorry, I made that mistake, yeah. So can you see this thing here is dx mu by d lambda, okay, along that particular curve, times this, right? And this operator, whatever I have, is acting on f. Does everyone agree? Right? What we did last time, and what I just showed you right now, is if I have my coordinate system here and I differentiate it and I ask how it changes, this is exactly our initial definition of, I think I erased it. Yeah, here. This is exactly our definition of what our tangent vector was. Right? So this thing on the left is what we call a tangent vector, which I will denote phi. It's our notation of velocity. And this thing here on the right-hand side, right, this differential operator, you can now see that this thing here is in fact a basis vector. That's what this is. So all I've done, okay, all I've done so far is I've said that we're going to expand essentially now a vector into this form. And all I've done is I've taken a directional derivative, and this is the definition, an alternative definition of a tangent vector. Okay, does anyone have any questions? Okay, so if you remember last time, we left off by saying that, one second. Okay, so if you remember the last time, we left off by saying that there was a crucial point that I wanted to make, that I'd said that we're taking a point on our manifold here. And we're going to see how it's separated from another point here. Can everyone see what I'm drawing right now? And we said that this quantity here, we're going to say that there's a separation between the two of them. These are events. Remember, points on a manifold right now are all given by a set of 4 coordinates, right? this is another set of 4 coordinates, but it's parameterized, for example, by lambda. Remember that points on our manifold are events, meaning a bomb blew up at 3 o'clock at this particular location, any kind of event. And the distance between them is our space-time interval, right? But here what I'm going to do is I'm taking this interval to be the separation vector. I'm going to call it that. And I'm just going to see this small step in this direction. I'm going to denote it ds. Okay? And if you rewind your notes back to what we did last week, I defined this in a very particular way, which you now see is almost like inserting my coordinate, choice of coordinate. This is, okay. And I said I'm going to choose my basis vectors. Remember earlier I just said that we can define our basis vectors as this, right? This is what we just saw in our differential operator definition. I'm going to say to this, I'm just going to add my separation vector. And this is going to be my new useful definition of what a basis vector is. And if you can now see this equation here, all I've done is I've said my separation vector is the separation in x mu times my basis. And this basis here is, remember, whenever I write this down, you're now introducing coordinates, okay, by this choice. I'm going to argue to you, and maybe I can leave this to you as an exercise. But the idea is, at the end of what we do, the last equation I wrote down for you last time was this. I took the length of my separation vector. Do you remember that? I said I'm going to look for ds squared, which was ds dot ds, right? And I said this thing is equal to, if you can write this out, dot which is e mu dot mu mu. Do you remember this? This was our last thing that we had written down, and we said that this quantity here is what we call the metric tensor. Like I said, this is just so far a recap of what we've done last week. Does anyone have any questions before we proceed?
Could you explain how the derivatives give out the basis vectors once more?
I explain what? It's a choice. It's a choice. All I'm saying, okay, so this is our choice. We're making a choice in physics. This is our input, as you will. So this quantity right here, what I've defined my basis vectors is I'm taking, if I have a point in my manifold here, I should draw this code. If my manifold is, yeah, this is better. Yeah, this is my manifold. I have a point here and I have another point here. And I'm just going to take the separation between them in an infinitesimal direction. Okay? This separation is what I call S or ds. Okay, it's an infinitesimal separation between one point and a neighboring point. And the choice I'm going to say is whatever I call my basis in my tangent space at this point. Okay, this basis is taking the separation vector and I'm going to differentiate it with respect to dx. Okay, and so if you guys remember this, this is essentially saying that if I have e mu, let me give you an example. This could be, for example, let's say x2. Okay, then I'm just going to take this differential and I'm going to sum over, if you remember the Einstein convention, and it's going to kill every single one because of essentially this returns a delta function. Yeah, this returns a delta function and it's killed everywhere except when e mu is 2 and the derivative is dx2. So all I've done is drawn for myself an orthogonal Cartesian set of basis vectors here. That's all I've done between this, and I've said I'm taking the derivative, and this returns a delta function. So that's all I've done. I've made a choice of basis, and this is the choice. It's a particularly useful choice for what's about to come next. And doing this, we've arrived at our space-time metric. Now, what you can do when you go back home is I'm going to assert to you that this definition is well defined, which is to say that if you change your choice of E mu, and you choose a different basis vector, you get the same result. This doesn't change. It's not dependent on our choice of coordinate. It works for any curve C. Okay, that's an assertion that I'm going to make. I think it's a good exercise to go back home and look and see. Okay, and so if you remember this was our invariant interval from special relativity. Yeah. So I want you to note something. Do you guys already see that there's a particular property of symmetry in this definition here? Draw that in a box, right? So from here itself, if we're defining this quantity, right? And we've defined it via the inner product. Right? This is the inner product. Can you guys see already that it's symmetric in its indices because the inner product is symmetric? Which is to say that if I replace this with this, I get back the same thing. It doesn't change. Yeah. So that's an interesting property that we've arrived at just by using the inner product of our basis vectors. Okay. So now I want to go further to start describing how we express a change of coordinates, because this is important. And after that, what I'm hoping to teach you guys in the next hour will hopefully solve the questions you've been having so far about tensors. You'll see that they're not scary objects to begin with. And all of the algebra that we're going to be covering now is of crucial importance to all of GR and of manipulating and working with tensors. Okay, so does everyone understand what my choice of basis vectors are? Like these are just, it could be anything. In this example that I've done for you so far, I've chosen it to be Cartesian in the choice. If I scroll up the choice, but you can replace it with any other basis vector, you'll arrive at the same result. Okay, so whenever you have basis vectors, that's when you're having a choice, but you have to make sure that it's well defined and works well under a change of coordinates. Which means the next thing we need to ask is, how do we express this basis vector, right, under a different set of coordinates? And it can be written out in a different by this way. So I can write this. Okay, so this might be a little confusing to you in terms of notation, but this is how I relate basis vectors to each other. So note here, guys, can anyone tell me how many equations I have out here so far? Just in this box, we're just looking at this red box. How many equations do I have?
The number of coordinates is 4, right? Because you have x, y, z, and time.
Yeah. Okay. So we're working at d-dimensional manifold. So if it's a 4-dimensional manifold, I have 4 equations. Can everyone see that? Because the choice I have, which determines the number of equations, is this free index on the left, which is a mu. So this is actually 4 equations, which I can write down entirely. So E0, okay, is I need these coefficients. And if I have these coefficients, I can understand how my basis vectors change. So now note that on the right-hand side, I have the summation convention here. Okay, so if I just write that out fully now, is this. Okay, does everyone agree with what this is? This is the same 4 equations that I had earlier. I've just written out the summation convention. And note how this, all I've said is my basis vector is I can write this as a combination of the other basis vectors that you may have if you're changing coordinates. These are the new ones, so I can write this with a prime, right? So what I've done is I've written it as a linear combination of my new basis vectors times what? What is this quantity on the left? These are just scalars. That's all it is. It's a scale factor. So I'm just scaling my new basis vector times something, times something, times something. And I'm saying that my old basis vector can be written in terms of the new basis vector in this format. Pretty simple, right? Any questions so far? So these components are known as contributing components. Okay, and you can do the same thing by introducing indices on the upstairs, which is that Okay, no, not yet. Okay, so now note that if I change and I substitute, I can go back. If I have it written in terms of this basis vector, EA, I can write this in terms of memes. How did I do that? I can write that as here. Yeah, is everyone clear? Does everyone see these two? They're just the same relation. All I've said is the same thing, that if I'm changing between one set of coordinates to another set of coordinates, all that changes is I have to write the basis vector, the old one, as a linear combination of the new ones. And the crucial components that determine this are these things that I call contributing. So what happens if I substitute this into that? So let's work that out. I can write E mu as E A mu E mu A. Does everyone see this? Can anyone guess? Oh, I made a mistake. I should have made this B. Yeah. So if I substitute one into the other, this thing here is now just a delta function. And I can write the other relation. So I'm just going to write down the 4 key relations from this bit so far. And if anyone has any questions on this, let me know now. So this is the way to understand how I can relate my basis vectors to each other. So the first one is if I write it in terms of, okay, the second equation is writing it the reverse, the inverse. The third is if I substitute one into the other. And the fourth is the inverse of this. Any questions? These are the 4 key relations that help us understand how our basis vectors change a change of coordinates. Any questions?
How would you find? So you showed the way they change, but how would you find the factor which you have to multiply to like see how they change, right?
Okay, good question. So we're going to use relations that we know about our coordinate system to constrain and understand what these are. And I'll show you these relations in a bit, but we know, for example, that this quantity is G mu nu. So that's one equation that we can use, and if we substitute this entire thing back into this, it helps us constrain the form of what this is. Okay, there's another relation which we haven't seen yet because I haven't introduced dual vector spaces, but note there's something. Note there's also a possibility of me doing this. Right? I haven't told you as yet what these basis vectors up here are, but there's a possibility for me to write this down. And if I know what this is, and you'll find out it's this, right? You can use various equations that you have to constrain what these components are. Okay, so that's the way that you understand. So before we go further, I just wanted to tell you how the metric can be used to calculate the lengths of curve. Okay, because so far, if you remember, we've not introduced the notion of a distance. Any other questions? Let's check the chat.
No questions so far. Yeah, carry on.
Right. So I think we should start by explaining how the metric can be used to calculate the length of the curves. Before we go on, I wanted to tell you that I've made a disclaimer at the start of this course, which is to say that from personal experience, when you learn GR, there are different levels that you approach a subject through. Like on the first go, you'd be bogged down in the mathematical definitions if you started with trying to fully, like I could have done this course explaining to you what a principal, fiber, and a bundle, a tangent bundle is, then define what the cotangent spaces to that are, and only through that explain to you how I define the inner product and other things. And the reason I'm not going to do that is because I think if this is the first time you're looking at GR, there's no need for you to be bogged down in those details. And it makes sense for you to learn to take some things for granted. and say, okay, as far as this course goes, I'm going to take this for granted, and I'm going to learn and understand the certain bits of this course. And when I want to come back to it a second time, maybe in the future, if I'm doing a postgraduate degree, I can learn those things that I didn't learn the first time. So I want to spend a lot more time explaining how we change coordinates, how we do that. So I've shown you how we can define a tangent space. We're going to assume that similar to that, you have a cotangent space that also exists. I can do this formally by explaining to you what one forms are and how you use one forms to build that space, but I don't think it productively helps us at this point in time. So I'm just going to say, similar to how we had our basis vectors with the index down, we can construct a cotangent space with that. But before we discuss that, I just wanted to talk about how we talk about the notion of length. Okay, and this is where we start. So now note that all I'm doing is I'm assigning our basis vectors that we had here, this quantity that we had. I'm going to say that these change for every point in our manifold. Okay, wherever you are, if you're here, it'll be x mu. If you're here, it'll be something else. To every point in our manifold, we're going to assign tangent spaces that we discussed last time. And with that, we also get basis vector. So this thing, okay, we're promoting not just like our, they're defined point-wise, but at every point, they return a vector field. Okay, so remember that. So our metric is uniquely defined by the point at which it's at. Okay, it's defined by the point along your manifold that you're at. Okay, that's what this is. Now, if we take how do we talk about the notion of distance? Okay, you remember we spoke about our separation vector earlier, right? If we take this and we integrate this along a curve, we should get our distance of separation, right? And that's what we're going to do. So we're going to take this. And how do we write this out? We found, well, the square of, we know what ds squared is, right? We know it's, here, it's this thing. Try to erase it. Yeah. The ds squared is g mu nu dx mu dx mu. Right? So it'll have to be the square root of this. Okay, so that's what this is. This is the quantity that helps us understand what distance is. But note that we have a problem. We can't simplify what we have on the right-hand side any further, right? Like, I'm not sure how we go about doing this integral. We have a square root and a modulus. It's a little difficult to do this. And you'll find that our initial definition of what our tangent vector is simplifies this problem to us. So if you remember our tangent vector that I called it d, which is defined as this, our separation vector d lambda, ds by d lambda, which, if you remember, we'd rewritten it as dx mu d lambda e mu. Do you remember this? Which is also written as d mu e mu. So I've just written my tangent vector in terms of my basis. Okay, and I'm going to take this tangent vector and I'm going to substitute that back into it. Okay, and when we do that, you'll find that you get this. Does everyone see this? And this solves our problem that we have, and we can move further, which is to say that the distance between 2 points on our curve is, if we integrate it along the curve, we get g mu nu t mu t nu, and at lambda, which is squared, comes outside as our measure. Okay. Now, I'm not sure how many of you were a part of the talk that Pugal gave last week about, I think it was about manifolds as well. And I think you spoke about special relativity. And I think Pugal mentioned this for the first time, that if you have a light cone, right? The light cone is important to us when we do relativity because it explains events that are causally connected and causally disconnected. And if you remember what Pugal had told you, he had said that if you have any path that's inside this light cone, it follows what's called a time-like trajectory. Do you remember? If you have something that's on the surface of the cone, it means you're traveling at the speed of light. It's called light-like. And if you're outside this entirely, it means it's space-like. And the takeaway from this is to say that if you have 2 points that are separated, you will know if they're separated by a time-like interval or a space-like interval. And you can tell for sure that if they're separated space-like, and they can't be in causal conflict with each other. Right? So that was the takeaway from Pavel's talk. Tell me if you haven't seen this before. But the point I'm going to make now is we get to make another choice which simplifies our physics. So till now, if you remember, I'd said that we have a manifold, we have a curve along that manifold, and it's parameterized by lambda, right? We can choose lambda in a certain way that simplifies our life. And what we're going to choose is that we're going to choose lambda such that when we integrate this, we're going to say that this tangent curve, right, will always be equal to plus or minus 1. Okay, it's always possible to choose our parameter in this way. So remember, this thing in here is a choice. Okay, what we're going to do is choose our lambda in such a way that this statement is true. Okay, the plus or minus depends on whether it's space-like or time, like we just discussed. Right? And if you've chosen this particular value of lambda, you may have read about this if you've done any TR before. This particular parameter is known as the affine parameter. Have you heard of this word before? Has anyone heard of this word before?
Nope.
Okay, but it's a very important parameter. If you've parameterized your curve by this way, it simplifies your the formulation in order for you to find the distance between two particular points. So we're going to do something. We're going to find the length of a curve with the following tangent vector as an example. Okay, so we're going to find the length of a curve. This is important because the rest of the physics that we want to do is contingent on us defining these things before we can move on to talking about differentiation. Okay, so the length of the curve, we're going to give you the two tangent vector. Okay, and we're going to say it's parameterized by between 2 points by this. Parameterized by this, which is to say that if I have my curve on my manifold, this point is lambda is equal to 0, and this point is lambda is equal to 1. Okay, and my tangent vector is as follows. Okay, can everyone see this so far? Okay, now just for this example, I'm going to set G mu nu equals theta mu. Working in flat, not even theta mu nu. Let's take it as Euclidean, just so that you guys have an understanding. We're looking to find the length of a curve now in our real world. And what we're going to do is we're going to use this, what we had said was our separation vector. We've integrated our separation vector. I've said that we've introduced a parameterization of our curve known as the affine parameter. And using this, it should simplify our problem into giving us a tangible distance between them. Okay, so does anyone want to work this out with me? We're going to just use this in our integral. Yeah. Okay, this is what it is. We need to substitute what we have so far into this. And we've taken this constraint. We're going to work in Euclidean space for now. We're not going to go on to Minkowski. If we can understand examples in Euclidean, it'll set us up to expand that further. So what would this be? So G mu nu, this thing, is just a delta function for it being the same. So if you have x and y, that's killed. So the only possible ones you have are dxx and dy. Okay, so you have dx, dy. Right? And this thing here is the square root of tx squared plus ty squared, which is what? It's the square root of sine squared.
Actually, we're not able to see that region of the screen. Can you?
Okay, can everyone see this? So all I've done so far is I've told you how we find distances. This is a crucial point because when we use the metric tensor, I've explained to you that the metric is useful because it helps us move between vectors and covectors. We've studied that before, raising and lowering. We've also said that a metric is important because if you feed in two vectors to it, it spits out a number. Okay, so we're seeing an example of that. We're seeing a vector where you have, there's a metric tensor and we fed into it two vectors there. And I claim to you that this gives us our distance. And this is the way that you find distance. And this is something that should be interesting to you, that in GR, we don't have distances that are defined intrinsically. The way for us to understand distances is integrating. And we break it up into small chunks, and then we work along the curve to find it. Okay, so now note crucially that the only way we were able to move further was that we've defined it at that particular point at lambda is equal to 0 and 1, but we're working in the tangent spaces to our curve. Okay, and we're doing this for an infinitesimal separation, which is to say that our points are in the neighborhood of each other. So this is a crucial point to make, but can everyone see what I've done? So I've taken my integral now. I've said that g mu nu in Euclidean space is just r Kronecker delta, which I think all of you have worked out from the various examples that you've seen. Which is to say that this integral is killed everywhere except for when mu and nu are equal to each other. So if they're equal to each other, they can only possibly have two values, one where it's x and one where it's y. Right? So this is our formula, which is tx squared plus ty squared, which simplifies down to the root of sine squared lambda plus cos squared. Right? Which is just 1. Okay? So if we integrate this, if you remember, our limits of our integral were between 0 and 1, which is our parameter, and d lambda, which is 1. So this is an example of how you can parameterize your curve in a manifold using the affine parameter. And you can see easily how this particular thing is useful when you're going to do calculations for yourself. Okay? Does anyone have any doubts so far? We've used our tangent vectors that we defined in the beginning for the first time. And using the tangent vectors, we've been able to talk about a notion of distance. Does anyone have any questions so far before we move on?
Where did the sine lambda and cos lambda come from?
It's input. I've given you an example of a question where here, if you look at what I've highlighted right now, I've told you that my tangent vector t is t mu times e mu. Right? Which, if you remember the Einstein Summation Convention, is tx times my x basis vector plus ty times my y basis vector, which I've given you in my question as sine lambda times my basis vector plus cos lambda times my basis. So this is the tx component. This is the ty component. And when you use that in our integral formula to find the distance, we find that this curve is parameterized such that the distance between the points is. Okay, so it corresponds with us, the curve being either space-like or time-like. So that's the point of this, that we can choose our parameter such that this holds true. And this works for any curve that you do. You can find such a parameter, it's known as the affine parameter. Okay, so now I want to move on to talking about our dual basis, because once we get our dual basis, I can prove to you that the metric lowers and raises. Okay, so if you remember our 4 equations right now, this is something that you probably want to memorize going into the next couple of lectures, but it's something like, or rather if you have it written down, it's fine. I'll tell you the fundamental relations. So far you could see that there are 4 fundamental equations I had written down with my basis vector. And this just told me how my basis vector changes with a change in coordinate, right? And the equation that helps me constrain what my scalar parameters are is the last 2. So the first 2 tell me how they change with the change in coordinate. The last 2 tell me how the components and the scaling components change, right? Meaning, let me just write that out for you. If you had 5i or 6j, right? These 2 things, e mu is just like the number 5. It's just a scalar. It's a number which scales your basis vector. So you can think of e alpha mu times e mu as, for example, 5i with the hat. Right? That's all this is. So this is my basis vector, and this is my scaling vector. So I'm going to do the same thing, and I'm going to tell you that just like we had a tangent vector at every point, there's a dual basis. Okay, it's called the cotangent space, and maybe if we have some time, we can come back to this. But Yeah, maybe I'll do a small aside. Does everyone remember what we had done with our Lagrangian mechanics? So I'm just going to do a small aside that isn't related to GR, but I think it's an interesting aside to give you right now. Does everyone remember what we did? Lagrangian.
It's like we shortlisted the kind of the basic parameters that we want to define the Lagrangian with.
Just this is an aside. So we're leaving GR for a moment. I'm just saying something to think about. Okay. And I'm going to come back to this maybe later if we have time because, okay. So I wanted to tell you that if we have a tangent vector at a point on our manifold, okay, at a point P, right? And what I did is I said, okay, for every point P in my manifold, right? This is my manifold, this is my point P. I take another point Q. Let's say I take another point R. I take another point here S. Okay, and I'm going to take every single point that I have on my manifold, and on each point I have my tangent space that's associated with that point. What I'm going to do is I'm going to sum over all my points in my manifold. And I'm going to take the union of my tangent space at that point. Okay. What I'm going to argue to you is what you get at the end of this is also a tangent space, but it's a very special thing. Okay, it's something called a tangent bundle. This is, I don't expect you to remember this. It's not important for GR. We're not going to come to this right now. But all I'm doing right now is taking my tangent space at one particular point, collecting all of them for every point I have in my manifold and taking the union. Okay, you get something that's called a tangent bundle. And if you can see here, it's intuitive to know that this tangent bundle is uniquely defined by two sets of numbers. The first set of numbers is explaining to me what the point is in my manifold. Okay, and the second particular piece of information that I need for this is to understand what my tangent vector is to that particular point. Okay, and if you remember what we had spoken about earlier, the tangent vector gives us our notion of velocity. Right? Does everyone remember? Our tangent vector is understanding is essentially our velocity. That was my second alternative definition.
Yeah.
For everyone that was interested in Lagrangian mechanics, all of you, do you remember when I started that talk, I said for Lagrangians, something that's important to think about is something called a phase space. It's a space that's a physical space, right? It's a abstract space that helps us understand the different configurations of our system. And we had spoken about this for quite a long time. We spoke about what is the minimum amount of information that we need to describe our system. And I told you how for different systems, whether you work in astrophysics or quantum mechanics, the phase space changes because you're working with different sort of observables. But do you remember for our Lagrangian what the phase space was made out of? What was the two bits of information we needed that we discussed? We said, we needed the position, right? And we also said we needed the momentum. So if you guys come back to what I've just written down here, can you all see that can you see this tangent bundle is uniquely defined by exactly that? You have a position here and a momentum here. So this is something that really I enjoyed learning when I was doing GR, which is that there's a fundamental relation between Lagrangians, okay, and functions on my tangent bundle. And there's a theorem that says you can define the Euler-Lagrange equations just through topology, just through this particular notion, which is to say that if you're tired of understanding equations of motions through looking at Newton's, those forces and understanding the different forces on a particular object, you can even do it the manifold route. And this, what I'm trying to say is that this is the equivalent formulation of the Lagrangian mechanics we've found so far. This is just expressing it via a different language. And if you're working on a particular problem, you might find that working through manifolds and explaining it this way might give you answers or make it easier to explain certain things that you didn't have earlier. So I just thought this is a small aside to tell you that hopefully you'd find interesting that you can even define objects in Lagrangians and equations of motion just by considering this thing called a tangent bundle. Right? I thought it's a pretty cool fact that we can talk about. Okay, so one thing that I want to do right now is discuss something called the dual basis. And the homework for last week, because I didn't give you any problems to work with, you all had to work with going and looking at that particular series on linear algebra. And I don't know how many of you did, but if you had done it, you would have seen that the notion of dual is not something that's scary or abstract, but it's naturally linked to a vector space. So if you haven't seen it yet and are confused about what duality is for any particular vector space, I'd suggest looking through the lecture series, and I'm pretty sure Bhargava will link it as I speak. Pugal loves that channel, so I'm not even looked at the chat. I'm pretty sure he's been.
How did you know that? Okay, I'll link
Okay.
both of those things. Just a quick
So if
question.
you remember what we started off with, okay, you have a question, yeah.
Yes, sorry. You mentioned about tangent bundles and all of those things. So you also talked about this symplectic manifold, this symplectic geometry thing, this lecture series. So we would find more about that in that series, right? Am I right?
If you wanted to do it, I can recommend 3 or 4 different reading sets, but I wouldn't recommend it as your first course to GR. I'd suggest spending this time working through what we're going to arrive at now, which is like Christoffel symbols and connections. And on your second course at GR, this stuff is postgraduate level. And it's not to say that it's unimportant or something that you can only comprehend at a later stage. It's just that it makes sense to look at it once you've worked out different Lagrangians, because then you'll say, okay, this is much easier to work it out this way than if I had a normal phase space system.
All right.
I don't know if that makes sense to you. It's just saying that you have time. You have time in your life to go through this. If you want to, there are 2 particular lecture series. I told you the first one is by Schuler.
Yes.
He does the same stuff, but what I covered today, he would have taken 6 lectures to do because he does it incredibly rigorously. And really well. The other one is probably if you're starting a postgraduate course, there's that symplectic geometry lecture series I spoke to you. That's also there. It's in both. And depending on how mathematical you want it to be, the closer you get to Schuler. So that's something to look at.
Right, thank you.
Okay.
Carry on. Yes.
Okay, so now we talk about a dual basis. So if you remember, we hinted at what this was in our special relativity series, which was to say that if I want an invariant length, right? Our invariant length, which was a number, right? If I had a matrix, I can't multiply 2 column matrices together. I needed to multiply a row with a column, right? That's what I needed. I need to multiply a row and a column vector together, which is to say that I need a method to move between row vectors and column vectors. And by now, I'm just going to see this again and again because it's important to not memorize, but understand that this is something that you have to look out for, which is that if you remember, we said that we're going to denote, simply put, row vectors like this and column vectors like this. But there's a lot more intricacies that's going on behind it. And the truth is that one belongs to our tangent space and the other belongs to its dual. It's the cotangent space. Okay? And what's important is that you have a metric that can take you in between these. And that's what we're doing. That's what a metric essentially is. Okay, but the dual basis is explaining or defining the same vector that we had in terms of the cotangents. Okay, so what I'm going to tell you now is just like we had our our basis vector here. I'm going to define my second set and define from my original tangent space my second vector with the following definition. And this is how we do it. It's just as simple. Okay, I take the second one. This is my new one, and I'm going to define it this way. It's a Kronecker delta. Okay, and this new basis vector that we have, which is defined in this way, say this is important. I can expand any vector that we had. If you remember, if I had a vector, I could take it in terms of its components times my basis vector. Right? This is me just saying if I had a vector v, I can write it out as 5i plus 6j plus 7k. That's all this is. But you're going to have this now in terms of a 4 vector. So you're going to be talking about 4 sets of information. You have x0, x1, x2, x3. Right? So I'm going to define this dual basis, and I can expand any vector I have in terms of the dual as well, which is just this. Okay, so you can see that they're related to each other. You will know that for now you remember from our special relativity discussion that as long as you're working where mu is 1, 2, or 3, you can do this fairly blindly, meaning you can raise x1 and write it like this. But the moment you have time, you might have a negative sign between moving between one and the other. Right? That was the minus sign in our matrix up here. Right? Do you remember? This is the thing that uniquely defines Minkowski space and separates it from Euclidean. Okay, so this is our dual basis, and all I've said is that I can expand the vector in terms of the dual. Okay, so now remember this. You remember we had a definition for our metric like this. This was our definition for a metric. It was the dot product of two contravariant vectors. Right? I can define a metric with the indices upstairs this way. So this is something we would have taken for granted, and through the exercises you would have seen, okay, I have a metric which I can use to lower and raise indices, but it's actually all the magic happens here. And you're going to see that this particular definition coupled with this, you can use this to prove that the metric in fact does lower and raise the same set of vectors. So we're going to do that shortly. Okay, so any questions so far about expanding it? Can you just see why it's called a dual? And do you guys see, do you have any questions on what I've written down? Because what we're going to do next is I'm just going to take the dot product of two vectors. Okay. And I'm going to just, because you can see I can expand my vector this way in the first way and the vector in the same equivalent way a second time. We're going to see the different ways that we can write out this particular product. And you're going to see this is the proof of what we studied earlier, which is the metric raises and lowers. You're going to see that. We're going to prove this. Any questions before we start? This is all that we have in front of us, and this is all we're going to be using. Any questions? None? Okay. So now note, what I'm going to start by doing is expanding both of these using 1. Okay. So how do I do that? Can everyone see what I've done so far? So V then becomes V mu E mu dot into it W mu E nu. Where if you remember, the good habit that we spoke about was that anytime you have repeated indices, you always use a new symbol. So if you remember here, this is the summation convention applied twice. And we've got two different sets of dummy indices. That's what they're called. Repeated indices are called dummy indices. Right? So now note that V mu and W nu are just scaling factors, like 5, number 7, whatever it is. So I can pull my vectors out through them. And I get E mu dot E nu. And I get, yeah, does everyone agree with this? And if you remember the definition of what our metric was? So do you see what I've done? All I've shown you so far is that the metric helps us implement the inner product. I can write out my length between two vectors in terms of my metric. And that's equivalent. I'm going to show you why I say that the metric is equivalent to raising. But does anyone, these are very simple steps that I've taken so far. Does anyone have any questions? What I'm going to do secondly is I'm going to use 1 and 2 together. I'm going to use 1 and 2. So V becomes the same thing that we have. Can you guys write this down with me? I should use 2. Can you guys write this out with me? What do you think the right-hand side is going to be? Because this is practice. That's why I gave you index practice so that you get comfortable doing this sort of stuff. You can pull the E's together, which is you're left with this thing here and this dot product. Which, if you remember from my definition of the dual basis, is just the Kronecker adapter. Does everyone see this?
Yeah.
Okay, so this Kronecker delta, what does it do? It raises and lowers indices as well, right? It just kills one of my indices. It tells me this is 0 unless mu and nu are equal, right? So it's this. Okay, so do you guys see something? I'm going to write this out actually as yeah. So now I'm going to we're going to repeat the same thing, just mixing the various other bases. We could expand this in terms of do 2 and then do 1, meaning you'd get v mu. You're going to write this out for me if you like. Yeah, you'll get just different products for this. Is this notation confusing anyone? Like I'm trying to give you more examples because I think from the first couple of lectures, then a lot of you are lost in the notation. Does anyone understand what we're doing? I'm just taking the same vector and I'm expanding it in terms of my different bases vectors. And if you do it this way, you'll find that if you write this out, you'll find that this, just do this for you. G nu, G nu. If you write out the third one, you'll find that this is equal to V. Okay, so does everyone agree on something that the left-hand side is the same for all 4 of the right-hand sides? It's just dotting 2 vectors. Does everyone agree? Okay.
Yeah.
I've just taken 2 vectors, I've dotted them, I've expanded the dot product in terms of different basis vectors. And all I've done is I've used the property of the definition of my metric as well as the definition of the dual basis. And I come up with 4 different unique right-hand side terms, right? So all 4 on the right-hand side have to be equal. So if I write that out for you down here, G mu nu, V nu has to be equal to. Does everyone agree with the last statement that I've made? They all have to be equal given that they're all I've done is I've expanded the dot product on the left hand side. So does everyone see if you break this up into 2, what does the left hand side tell you? It tells us that this metric lowers the vector. And the right hand side tells you that the metric here raises. Can everyone see the proof from this? Any questions? Okay, I think we want to move to tensors first before I come back to the change of coordinates, because I think that's something that all of you wanted to think about. I'm going to show you just how easy tensors are. Like if you've understood this, all I've written on this is 1 page so far, you guys are fairly far ahead in understanding what a tensor itself. Does anyone have any questions? Because all we've done so far is I've used the inner product and I've expanded my vector in different bases. The first basis was when both vectors, let me highlight for you. First one is when both vectors are in the same basis, lower. One is a mixed one. There's another mixed one, but in the opposite order. The last one is when they're both in the cotangent. Is this calculation here clear to everyone? Is there a question that anyone of you have?
Yeah, it's clear.
Okay, so now we're going to get to the the one missing piece that you need. And if I give you this missing piece, you should have understood tensor. And that is the definition of the outer product. So the outer product is something that complements the inner product. Okay, you can think of the inner product between two vectors as the action of one of those vectors on the other, which is to say that if I have u and I dot it with v, just think about this in terms of notation as u acting on v. Okay, this is just notation, right? What this is that u is a linear function that maps its argument to a real number, such that this is the map. So can everyone see why I've written it this way? This is notation from like analysis. I said that u, which is a vector, is a linear function that
Chinmaya, are you there? Can you hear us? Because your live stream is loading.
Is he offline? Hello.
I can't tell if he's offline or online, but
He lost power at home.
oh
He's
yeah,
put up in the chat.
it's
Oh,
So he's in Chennai, right? So if he's in Chennai, he will get the power back immediately. The chances are high. Any questions?
Rishi.
Can you guys hear me?
Yeah.
Okay, great. Okay, pause back. Just connecting. Just give me a second, and we're good to go. Okay. Hopefully, this. Just wanted to tell. I thought for a change, I'd walk you through calculation rather than giving it as homework. But what we just saw right now is extremely important. And if you understand this, I'm not joking. This is all there is to understanding tensors and outer products and all of that. Everything boils down to the four things we just did right now with vectors. I tried to build that skeleton for you. So let's just walk through that. Hang on. Okay. See one note. Okay, is everyone here with me?
It's loading. Yeah, I'm able to see.
So this that we've done right now is a fundamentally important calculation. And if you understand this, tensors in 5 minutes will be the easiest things you've done in your life. Okay. So remember, all we've done so far is said that whatever we had a basis vector of here, we're going to dot it with something new, which belongs to its cotangent space. And we've defined this product is this. That's how we define the tangent space. And from this, I've just used this definition that we have here to expand vectors in two ways, one in the tangent space and the other in the dual tangent space this way. Okay, you can think of it that way, that if you have the basis vectors with the index down, that's in the tangent space, and if you have the basis vectors with the index up, that's in the cotangent space. Okay, and you've seen before that if I dot two basis vectors that are in the same space together, that forms my metric. And I also get the metric upstairs as well. And all I've done is I've applied these two equations here, and I've written out my vector to a dot product between two vectors as in terms of the different ways that I can expand them in terms of their basis, right? And I've argued to you that you get four different results. One where you have both the indices down, one index up, one index down, switch them, and then both index up, you get four different results. Can everyone see that? You get four different ones here, and they all have to be equal because the left-hand side is equal. We're dotting two vectors together. And what you arrive at is the proof for why the metric tensor raises and lowers. Or it's the proof for why the metric tensor, you can call it, is a pushback or a pullback or a push forward, meaning it sends a vector to the co-vector space and vice versa. Okay, so the jargon doesn't matter. I think the easiest thing to do in the calculation, the only mathematical steps we've done is to group the vectors that are dotting with each other and pull out all the scalar coefficients. So if you can see this, I've depicted an arrow over all the vectors. I'm going over this again because this is a step that I want to make absolutely clear before we continue, right? So the vector, I've just expanded it in terms of the basis vectors times, and I'm going to highlight the scaling component here. So this is like I hat, and this is like the number 5, right? So even here, you can see this is the scaling factor here, and this is the actual dot product between the vectors. And that's the same thing here and here, right? So like W with the new upstairs is just a real number. It's a component of the real number, right? So does everyone understand this calculation that we've done? Because if you understand this, tensors are easy. Does anyone have any doubts? Like, I hope this should almost be elementary. Even though we've got a lot of indices written out here, hopefully this is elementary. Is this clear to anyone? Or is there any doubt that you have? Speak now. Is it clear? Could one of you say?
Yeah, I think you can.
Okay, good. Now we get to the outer product. And the outer product, before I do it, I'm just going to tell you a notation that's often used in literature and textbooks, which makes sense through analysis. Okay, and where we got cut off was I was saying that all I'm doing is I'm going to rewrite my dot product as two vectors in terms of a function taking another function and spitting out a number. Okay, so what I'm going to say is I've defined a map, okay, which takes, I'm going to call it U. What does it eat? As an argument, it eats another vector. Okay, so I've got a vector here. which eats another vector here. And what does it spit out? It spits out a real number. And what's that real number? It's the dot product, right? Like if this is 5i plus 6j, and this is what I'm going to call u, and I'm going to say it eats in its argument, let's say 7j plus k. Okay, and I've said the result of this thing is just the dot product. Okay, that's what we're going to get from this. It's going to be u dot v. This is just notation at this point in time, but I'm going to write it in terms of the brackets here. So whenever I see a dot product from now on, instead of writing u dot v, I'm going to just write this as u in brackets v. But it should be obvious now. Okay? Why have I done this? Because can I create a function, okay, just like this, which in its argument here, where v is, right? So right now I've got u, which is my function. Can I have a function which takes here in its argument, instead of v, what if I have not one vector, but what if I have two vectors? So if I have some function that takes u and v in it and spits out a real number, is there a function that exists which satisfies this condition? Yes. And this is all what a tensor is. That's all. It's just this simple. Okay. So we're going to construct these new objects by something called the outer product. Okay, so the outer product is a symbol that's quite painful to draw. So can you all write this in your notebooks? Because I don't want to go through the pain alone. I want you to be in this with me. Because you have to write your symbols neatly, okay? And I think writing the dot product is super simple. But if you were to write the outer product, it's quite painful. It's an X with a circle around it. Okay, that's our outer product. I want you all to write it with me. The outer product. There you go. Okay, the outer product is defined in this particular way. So remember now, we're looking for some object which takes in two vectors into its input and spits out a real number. Okay, and I'm going to say that I'm going to call it P outer product Q. And I'm going to say this is my new function. Okay, and I'm going to define it this way. So if this eats a vector U and a vector V, I'm going to define it such that you get P dot U times Q dot V. It's just that simple. Okay, does everyone see this? It's just notation at this point. And I can write this as, in our earlier notation, it's P and in brackets the first vector, Q second vector, which is equal to the thing above. Any questions so far? This is what our outer product is. Okay, and do you remember earlier I told you there's a property of my metric where the indices are symmetric. And where did I get this claim out of? I said it was a claim initially, but how do you prove it? You prove it because if the metric is defined in terms of the dot product, right? If you have the dot product right now, if I interchange the indices here, the dot product doesn't change, right? 5i dot 6i is the same as 6i dot 5i, right? So if I interchange the indices, my quantity that I have here is still the same, which is why the metric tensor is symmetric. That's the first thing we said. Can I say the same thing here? So if I have my outer product P and Q, right? Is this the same as Q cross P? Is it the same? It's not, because you can see clearly it's like the first one is paired up here and the second one is paired up here. So if I have Q cross P and I input two test vectors, U and V, into this, I'm going to get Q dotted with U times P dotted with V. So it's not the same at all. So can you see how the outer product for a tensor is not symmetric unlike the inner product? That's the first thing to pay attention to. Okay. Also remember that this cross is not the vector product. The vector product, if you remember, you have to write it out as some sort of matrix where you have the first one, the second one, and ijk, right? That's what the vector product is, the cross product between two vectors. This isn't that. This isn't the cross product because you're not getting a vector at the end of this. You're inputting two vectors here. You're taking the dot product of them, and you're getting out a real number. Whereas if you remember the cross product from the vectors that we learned, you get a vector at the end of it. So does everyone realize why the outer product is something new and is something you likely have not seen before? Right? Does everyone agree? So now we're going to just do a very simple example. So whatever I give you, remember if you have a tensor that's now defined in terms of the outer product, you feed into it two test vectors. And in our case, the test vectors were just U and V. U and V were our test vectors, and P and Q was the outer product. Okay, so I want to show you something. There's an example which you may have seen. Pugal, I think I saw in his talk on tensors. I told you something that if you have a tensor and you have, I think he was walking you through the different properties of tensor, right? Mm-hmm. And he had said, well, it scales this way. He had said this, right? Does this look familiar to you? If I have a scalar in my argument, it's just the same as taking it out. It doesn't affect it, and I do it here. So how do I define it? Let me just say H is defined as U cross V. Okay. So now if it's U cross V, let me pick someone because I want an answer from one of you, because this, if you understand this, you understand tensors. So I'll take Mokut. Okay. So remember our definition of outer product above here, right? The outer product was, I'm going to say, and to that you input two test vectors. Right? Okay, so in our new case here, I've said H is U cross V, outer product V. What is, how do I write out this? What is H, P, and Q? This, hopefully, the moment you figure out this example, you'll see, oh wow, like outer products are so easy. So I've given you what H is, and all I've said is you're going to input and feed in P and Q into H. It'll tell me what the answer is.
So you'll have UP U dot P times V dot Q.
There you go. Just that simple, right? Super simple, not complicated at all, right? That's all we've got. So our outer product, as you can see, is here. So how can I prove that if I have alpha in my outer product, why does it come out here? As in, I have to essentially prove that it's equal to this. And you can see this is true from the linearity of the inner product, right? So if I now have, so let me just write this out fully, because for anyone who may have a doubt, this should be clear. So I'm going to say H is defined as U cross V. Okay, this is my definition of what H is. And to H, I'm going to feed in, U cross V. Into this, I'm going to feed in two vectors P and Q. Okay, so if you remember, the formula for this was that if I have the outer product, it's so simple. I'm just going to dot the first one and dot the second one and take it. So U dot P times V dot Q, right? That's what this is. That's our outer product. But now guess what? We've asked the question, what if there's an alpha in here? So what is H of alpha P comma Q? Well, this is now U cross V, and I'm going to feed in now alpha P Q. So what does this look like? Well, it's U dot alpha P, right? Times V dot Q. But if you remember from vectors, if you have a dot product, the alpha can be pulled out. So this is just equal to alpha times U dot P and V dot Q. Does anyone have any doubts? I think Pugal mentioned this property of tensors, right? So this works both ways. Like if you have H of P beta Q, this also works. As long as there's some number, it doesn't have to be alpha and beta, it could be 5Q. You can just pull that out. Okay, so now finally we get to what a tensor is. I hope now you say, okay, tensors are so easy. I don't know why I spent 3 weeks wondering and worrying about what they are. Okay, so a tensor is the object H, okay, which is U cross V. That takes two vectors in its argument. I'm going to just write this out for you. Its arguments and returns an output a real number. That's it. That's the definition of a tensor. This, by the way, is the example of a rank 2 tensor. Why is it rank 2? 1, 2. Okay. So what is a rank? It's just like you need a way to classify your tensors, right? So a tensor can be classified as rank 0, rank 1, rank 2, all the way till n. And this is just because this was our definition of our tensor. Rank 0 just means, well, it's something which doesn't have an outer product inside. It must be a scalar. Okay, a rank 1 is h is equal to u, but we can't have an outer product because we don't have a second vector, right? So now remember what we had said. Well, if you have u, this is now a tensor, right? Acting on v, what will this be? U dot v, right? What does this mean? Well, a rank 1 tensor is a vector. Does anyone see why it's called that now? You may have heard of this or read about it in your previous discussions, but this is proof of where this comes from. What is a rank 2 tensor? Rank 2 tensor just means that there are 2 vectors in the outer product. So what could you expect a rank 3 tensor to look like? You'd have u cross v cross w. And what does that mean? It means that it will input 3 vectors. Now, it eats 3 vectors to give you a real number. So in general, you can have a rank n tensor, which takes like cross, cross, cross. Right? It takes any number of vectors from 1 to n. I've written this alternatively. So 1. Okay, it takes n such vectors and returns a real number. Right? Does everyone see that? So now, for example, if I told you now that in GR, if I have something like G mu nu, immediately you can tell me, okay, that's a rank 2 tensor because it has 2 sets of indices. If you remember, I started off this lecture by saying we're going to be interested in a quantity called the Riemann Tensor, right? Immediately now you can see, okay, you can expect that this quantity, whatever this tensor is, has to be defined in terms of some outer product. And all it does, super simple, is whatever the outer product is, it's going to, how many vectors? Can anyone tell me how many vectors this quantity R, mu nu, lambda rho eats? What rank is it?
It's a rank 4.
Rank 4, super simple, right? So hopefully you understand also why rank 0 is a scalar, because there doesn't exist an outer product because there's nothing to work with. It's probably like a trivial example of a tensor is a scalar. Rank 1 is a vector because you only have u. You don't have a v, but we've worked with the previous definition that if you eat an argument, you dot it. So a rank 1 tensor is a vector, and from rank 2 the fun begins. This is all a tensor is. You're just taking a dot product. It's that simple. Okay, so there's another property maybe Puran has told you about. And so for this example, we're going to work with a rank 3 tensor. I'm going to call it T3. Okay, so if T is a rank 3 tensor and I have 3 vectors, U, V, W. Remember, if it's a rank 3 tensor, it must eat 3 numbers in order to determine a real number. What's my notation? T, which is my rank 3 tensor. U, V, W will be a number. Right? Now, there's a couple of properties which you can now, can I ask you to prove this? And if one of you who hasn't spoken yet, you can tell me immediately how you think you prove it, right? I claim, write that here. I claim that the tensor has this particular property, that U plus V, comma, V, comma, W. Okay, we're working with rank 3 tensor right now. I claim that this is equal to T of U V W plus T of V V. This is my claim. Can anyone tell me how you'd go about proving this? So I want someone who hasn't spoken yet, Apurva. I just want you to tell me when you see this equation written down now, what do you think about? Yeah. Apurva, can you tell me what you see?
similar derivative with the matrix, 3 by 3 matrix.
I can't hear you. I think your connection is off. Something's off.
Oh, am I audible now?
Yeah, better, much better. Tell me. What do you see when you see this equation?
Whatever. Okay. So they have written those two, that one matrix in terms of two different matrices as
One matrix in terms of two other matrices. We've not spoken about matrices here so far. I've just mentioned it as a function. So let's not call it a matrix yet. Let's just talk about it in terms of a function. I'm asking you, when you see a quantity like this written down, what do you see? Now, we're just going to go turn by. What do you see in this?
it's a function involving three different.
Okay, what rank tensor is it?
Can be
It's rank 3. Yeah, you're right. Rank 3. You can see because it's eaten 3 vectors in its argument. I want you to also note that this thing that is written down here is actually shorthand. And it's shorthand, remember now, it's just simply saying it's the first vector dot u times the second vector dot v times the third vector dot w. Can everyone see it from this definition here? That was our definition of what the outer product is. That you take the first vector and in this format and you just dot it, second and third, right? Can everyone see where you get the proof for this plus sign? I've
but
said
Chinmaya have got a doubt with the rank because in the 1 blue and 3 brown, in that series, they define rank as the number of dimensions that we get after a particular transformation is being performed to that particular vector. Over here, it need not be each 3 vectors. It need not be a rank. It need not be rank, right? Like it depends upon the output.
okay, yeah, that's true. In that, okay, so I've done it in terms of shorthand, saying that you expect this thing to be a rank 4 because you see 4 different ones. But you're right in saying it's in terms of the output because if you have something that raises and lowers, you can't tell just by looking at it this way. But the way you understand that it's a rank tensor in general is by looking at the outer product. Okay, and the
Yes.
tensor by definition is rank n, depending on how many such terms you have in the outer product. Okay, so this is where you look to see where the rank is, but in general, we can be lazy and say, here, this is rank 3, because for now, in this example, we're going to look towards getting a real number. But you're right. In general, the rigorous way to see where what the rank of a tensor is, to look at the outer product definition. Okay, so remember, this is my definition of tensor. Okay, and this is my use of tensor. Okay, I define my tensor in terms of an outer product, and I use it by feeding it vectors, and I get things out in as an output. Okay, so can you see why this has a plus sign? Because it's a plus sign which is inherited from the dot product, which is to say that if it was PQR, you'd have P dot U plus V, right? Times Q dot V times R dot W. Does everyone see this? And this linearity of the dot product means that you get this plus this. I'll leave this as an exercise to you. Just take this down if you like. Yeah, this is my claim. I think the proof shouldn't be more than one line, but you can do this at home. Okay, so why are tensors of fundamental importance? So tell me so far, remember now, if I have a vector here, okay, so I'm just going to take my tensor that I've drawn in this box here. Can you see my U vector here, right? When I have this U vector here, it's an abstract vector so far. Have I, say yes or no, have I defined any set of coordinates so far? We haven't. We haven't written out any coordinates right now. The moment you expand my vector into a set of components, u mu times like this is our choice of coordinate, right? So the idea is that whatever I've written out so far in terms of what a tensor is and defining it in terms of outer product, it's important because they're defined without any reference to coordinates. So if we use these objects right equations for physical laws, you'll end up with a set of equations that are valid in all coordinate systems. And this is the principle of covariance, that our real world should not be dependent on our coordinate system and choice. This is something that I've been telling you each week since we started learning special relativity. Okay, so you guys can see something now. Like hopefully you'll see what's coming next. But the idea is, so far we've spoken about vectors. And just like we had vectors, we had a dual vector, right? But so far, I've only spoken to you about what tensors are in terms of this outer product. How do I, how do I generalize my concept of a tensor to include both lower and upper indices? Or rather, how do I include both, eating both a vector and a dual vector? That's the question we're going to do now. And hopefully, is everyone clear on the idea of the outer product? That a tensor is defined in terms of the outer product. Here's what it is. Takes n number of vectors in its arguments and outputs a real number. That's my definition of the tensor. It inherits the definition of my outer product, which is just simply saying that I'm going to feed it certain vectors. You take the first vector and dot it with the first vector in the outer product. Take the second one, dot it, and on and on. Right? That was the exercise we did so far. I hope all of you are clear with this outer product. It's super simple, right? It's just like the inner product that we've been comfortable with. It's just like a generalization of the inner product to multiple sets of vectors. Okay, so now what we're going to do now is we're going to express, just like we did when we expressed our vector v in terms of two different ones. Right? Remember we did this, which is the same as this. Right? I'm going to construct a tensor basis. And what am I going to do with my tensor basis? I'm just going to construct one which helps me express my tensor. So far I've said my tensor T is something. It could be an outer product. I'm going to take a rank 2 for now. It's this, right? But instead of writing it out this way, I'm going to expand this T into my basis, just like we did for vectors. Okay, does anyone have any confusion about what's coming next? Hopefully this is something that should be clear and will make more sense. Can anyone guess what the next step is? Can anyone guess what the next step is to generalize my expand my tensor into a basis? And if I were to ask you to do that, the place I want you to be looking at is here. So if I change this, and instead of writing my outer product in terms of P and Q, if I write my outer product in terms of this, now you have a tensor basis. So I want to make it a point that up till we've worked here so far, till here, whatever my tensor is, if I expand it in terms of a vector, right? This is coordinate independent. So just like we introduced a set of coordinates to make our life simple and go onwards by saying a vector P is P mu times E mu, I'm going to do the same thing now with tensors. So it's only at this point, after my definitions are done, is when I'm introducing a change of coordinates. Introducing coordinates. And you can ask me how these things change when we look at it from a different change of coordinates. I plan to do that if we have time today, or we can do that soon. So I want to do this now. I'm going to talk about expanding our tensor in terms of a basis. I'm hoping this is all new to you, and I'm hoping this is exciting because it should simplify concepts that you've been reading about. And tensors aren't scary anymore. That's our definition. You've defined it via the outer product, and it just eats vectors and spits out real numbers. Okay, so now we will define it in terms of a basis. Okay, so for a tensor of rank n is made up of a basis of outer products. And we're going to do it this way. We're just going to say it's EA cross EB cross all the way EN. That's it. So that's how we're going to expand that tensor into this basis. And just like how we saw, just like how we expanded our vector in this way, right? Hopefully this is now natural that if I have my tensor written out like this, I'm going to expand it in terms of some components. Where earlier we had the component P mu, there should be some equivalent component for T, and I'm just going to say whatever these are, ABCs. Remember, they have to be summed over with the Einstein Summation Convention. Can you see here that if my basis vector is E mu, right? I've contracted it with my scaling component p mu. So here, if you can see my tensor is comprised of A, B, and C, or till all the way to N. I'm going to expand it this way. It's just like this. So I'm going to take an example of a rank 3 tensor just for now. Okay, just for now, it's an example of a rank 3 tensor. Does everyone see this? Hopefully, this should now be, you should almost be expecting this. I sync, notebook hasn't synced yet. Can everyone see? Oh, it's okay, it's syncing now. Yeah, can everyone see now? It's loaded.
Yeah.
Does everyone see? All I've done is I've generalized my expansion of a vector into my basis. What does that mean? It means that if anyone needs a picture right now or is lost, I'm just going to draw that for you. Be anything, any observable in the real world. It doesn't care who I am, right? It's existing in its own world. What I'm going to do is when I say I'm introducing a basis, I'm saying I'm charting and trying to find to actually do the differential geometry we've done it, which is that this vector. When I see this vector in my coordinate system, maybe it's pointing this way. All I'm doing is I'm charting out this grid, and this grid is what we call our basis vector. That's all this is. So the smallest grid unit I have in this line is E0, and this can be E1. So if I had to describe this vector that I have here, which I helpfully drew in black, that we have a vector here, right? So this is E0, this is E1. How would I describe my vector? Well, it's 1 step, 2 step, 3 step, 4 steps to the left. So it's 4 E0 and 1, 2, 2 E1. Right, so my vector V in my basis now, I've expanded it as 4 E0 plus 2 E1. Okay, and guess what these are? This, when I said a vector can be expanded in terms of V mu, P mu, I've given you a two-dimensional example, which is V0, P0 plus, why did I write P? V0, E0 plus V1, E1, which in our example, what is it? Well, V0 is 4 and V1 is 2. Does anyone have any questions? Is this clear? Right?
Yes.
I'm just taking the same, I'm not going to erase this, like stop me if I erase things because I think I've done it too quickly. I'm just taking the same concept that we have here and I've applied it to my tensor. I've expanded my tensor on the basis, and just like how you have these scalings, right, like 4 steps to the left, 2 steps up, that's what this is. And if you look at this equation up here, you'll see that this is in fact a large sum because remember the summation convention applies. So this could be T001 and you'll have E0 cross E0 cross E1. It's some complicated long, like many terms, which I've just written it out this way. Some of them will often be 0. How it plays out is you have to work that out, but depending on our definition, this is what it is. And these components T, A, B, C are just here, the number 4, the number 2. And they've changed, right? Like it's number 4 for this one, it's number 2 for this one. Similarly, for a particular combination of A, B, and C, you'll get a corresponding unique number here. For another A, B, C, you'll have another number. Yeah, that's all we've written. Okay. Now remember, just like my vectors, I could have constructed using my dual basis, which is instead of writing it as E0, I can write it as here, up here, right? My tensor, I can expand this way. Right? Okay, Pugal's power went off. I've solved my problem. I've opened chat on my phone. So at least that I can see. Okay, so you guys can see all I've done. Pugal, use your imagination. Stephen Hawking can't write, so he used to, yeah, it was all in his head. I think you can do that too, even if the power went off. So just like the basis vector, we've expanded it both in terms of all the indices down. You can have a cross product with all the vectors up. And that's the equivalent definition. They're the same tensor. It's the same tensor, just like our vector v, I could have expanded it two ways, indices down and up. The tensor is the same tensor at the end. It's my perspective that's changing. Okay. Finally, let's construct an explicit example of a tensor, which is our metric tensor. So G, okay, is constructed from G mu nu. We're familiar with this. We know what this is, right? G, which is our metric tensor, is constructed out of G mu nu times this. Okay, this is not just for my definition of what the metric tensor is. Does everyone see what the outer product is now? So can anyone guess? So if I had two vectors that are input into this, which is G times U and V, right? What do I get from this? Well, this is now G mu nu E mu cross E mu, right? And to this, I add the two vectors that I'm feeding it. And if you remember my definition from the outer product, it's just dot the first vector and dot the second vector. What does this become? Well, it becomes G mu nu times E mu dot U dot. Okay. And guess what this is? I'm going to simplify this further for you. So E mu, I can expand my vector U in terms of another basis. And I'm going to do it this way. V is already done. So rho times U rho. Okay. And similarly here, I have mu dot E sigma V sigma. Yeah. Okay. So now, does everyone remember this property that if I had E mu dot E mu, this was just the Kronecker delta? Well, you can see here, I've got that same property here and here. So this thing that I have right now is G mu nu times delta U rho and delta V sigma V sigma. What does that become? Well, this is just G mu nu. This is the Kronecker delta, so I get U. Oh shit, I got it. Okay. Can everyone see now? Does everyone see? This hopefully should clear up what tensors are. I've given an explicit example, so I'd say write this down. I'll walk you through this one last time if it's something that I think it's important that everyone goes through. Big red box. So our explicit example for a metric tensor was G. I've expanded G in terms of a basis that we call G mu nu, and it has an outer product of two basis vectors E mu, as you can see. You'll now realize that the components here are some things that we've seen before. Right? Like we've seen these components before. Like if this was eta mu nu, you'd know what these are. Right? But it changes depending on the space that we're constructing. So if I feed in two vectors now, right, you can see this essentially gives us our invariant length. So walking you through the calculation, I've just expanded G in terms of the outer product. I've said, well, it's eating vectors U and V, right? So that's what I've shown you here. Then I've said to simplify this further, U I've expanded in terms of its basis vector, V I've expanded it in terms of its basis vector. I've used the property that when I have a vector that's dotted with the basis vector and its dual space, I end up with a Kronecker delta, which I've used here. And you remember that that knocks out and kills all the indices except where they're equal. And we end up finally. So I've proven to you that our definition of the outer product does exactly what we're talking about. it acts on the metric acts on two different vectors to give you the dot product. Because if we're done with this, I'm just going to list out a few properties of tensors, and we're done, and we can move on to connections, which can talk about that. And I think it's already been 2 hours, so it depends on you guys. We can even do connections the next time, and there's a lot you can do with this to revise. I think that might be better. So just to give you, hopefully you've seen now what tensors are and what they do, how they're defined in terms of that outer product. I think it's the simplest way to think about them. And so just as you remembered the calculation we did with the vectors, which is that a vector can be expanded in terms of this way, which is equivalent to it being expanded this way, right? You can do the same thing with the tensor. And I'm going to say that this tensor T, where it eats two vectors, is the same as this. Which is the same as this. And you can even do a mixed tensor here as well. Can anyone tell me what this is? Does anyone know what this is? This term here, how would I define a tensor in this way? So far we've seen that a tensor can be expanded in terms of T, A, B, C. And then you have EA cross B cross. Yeah, I've shown you that you can have a mixed index this way as well. So what do you think a tensor that looks like this has? It should be fairly obvious to you now that I'm just contracting the indices. Can you see now I have a mixed tensor, one that has here. Let me highlight that for you. We've got one residing in the dual vector space and two that are in the normal tangent space. Can you see that? It's the same tensor at the end of the day. There's no difference. I'm just expanding it in different spaces. So when you see something like this, right? When I'd shown you what this quantity is, right? There's no difference. You've learned it now. I've just relabeled T to R and said like it's some special tensor, but essentially that's what tensors do. This R here will be taking, it'll eat 4 different vectors to give you a real number. But you can tell clearly that because it's a mixed index, can you see the difference between G mu nu and something like this? Right? If you have a mixed index, for example, when you have a mixed index, it just means that in its outer product definition, you just have a mixed basis here. Some bases have the index up, some have the index down. So can you see that? And if I apply this here, what do you think this curvature tensor is defined? Well, it's just defined, it's some tensor R, this times E mu cross U. Does everyone agree? That's all this is. And it tells you that it needs to eat these vectors. So that's all the tensors are. Once you've understood this here and understood that you can expand tensors in different bases, you understand that tensors are defined in terms of this operation here called the outer product, which is inherently related to the inner product. Then now no longer do these quantities like this appear mysterious. That's our rank 2. You can immediately say that's rank 2. It's called the metric tensor. You can see that there's some special tensor like this. This is also rank 2. You'll find that there is T mu nu. It's another rank 2. If any of you have done electromagnetism, you'll see that the tensor of electromagnetism is something called F mu nu, which is also a rank 2. You'll see that the curvature tensor okay, does everyone see this? It's not, there's nothing more to it. It's just the outer product. but there's a dangerous, there's something that requires caution, which is why I want to talk about change of coordinates later. So before I take any questions, I just want to say this last thing, that tensors are defined by this outer product here, okay? But not all things that have the index up, for example, are vectors. This turns out to be a vector. But if I collect, I can do crazy things at the same time, right? Like I can collect 4 random bits of information. Like I'll call this thing Pukar. I could call this Apurva. Just 4 random numbers and 2 others like Ashmi and Mukund, right? And I can say, well, this new thing is something that I call V new. And whatever value of new I get back 4 names. Does this make it a vector? It doesn't, right? Because there's no meaning to this apart from having a collection of 4 numbers. Which is why I think some of you, I tried telling you that the best way to think about vectors or an important way to think about vectors are under its transformation property. Meaning a vector is something that transforms in a certain way. Like when you look at it from a different coordinate system, it looks in a particular way. And that particular way is that if I want to get to this later. I don't think we have time today. I think you've taken a lot in. But I wanted what I wanted to leave you with is to say that not everything with indices is a tensor. And a fundamental quantity that you're all going to be working with is the symbol for gamma. So you're going to see this again and again and again. And it's a very special symbol. It's called the Christoffel symbol. Okay, this Christoffel symbol is something that helps us understand. Like I told you, if you have a curve and you're trying to find the derivative, by moving from a point to another point and asking yourself how that's changing, you can't take derivatives in general in GR because you can't compare these 2 vectors. There's no way for you to do calculus. So to do calculus, you have a vector space here, you have another vector space here, and you have to find a way to connect between one and the other. And the way to do this is something called parallel transport. Okay? And this thing, the intuition for it, I think I'll go into another time because it's something I want you to all be fresh and concentrate for. But the way you do it is by finding these things called Christoffels. And once you find them, you can find your normal derivative. And to that, you can add your Christoffel symbol. And this thing is essentially how you take a derivative in GR. Okay? So I'm not defined what this Christoffel symbol is, but you'll find that this Christoffel symbol will have two symbols like this. Okay? And while it has symbols like this, you'll find that this is not a tensor. So what I wanted to tell you was that eyeballing a particular quantity, seeing that it has indices up and down, right? Unless you know what you're talking about and there's a definition at hand, we can't assume that this thing is a tensor. Okay, because one half of the puzzle is this thing that we called the outer product. Okay, but the second thing that you need to call it a tensor is its properties under a change of coordinate. And we'll find out that tensors transform in a particular way. Okay, and meaning that if I move from a coordinate system that is like this, if I move from this to, let's say, that, right, and this is my new coordinate system, the object that I'm considering has to transform like a tensor as well. And if we know how that transforms, and it transforms the way I prescribe the definition of, okay, a tensor, I'll say it transforms in a very particular way. Okay? So you'll need to satisfy both of these criteria before you can call this thing a tensor. It has to have a certain definition with regards to an outer product, and it has to transform under a change of coordinates in a certain way. Otherwise, it's a quantity that isn't a tensor. So this is just something I wanted to caution you about. And this is the reason that I wanted to go into change of coordinates, even though it may not be like a particularly interesting topic at the face of it. Why do we want to study how things look in a polar coordinate system or any other coordinate system? But the point to note is that things that we call tensors that are fundamentally important to us may really not be tensors. So that's why this is important, and I think we can do this next time. And we'll find that objects like G mu nu transforms just like a tensor. We'll find objects like this R mu nu, T mu nu that we discussed in GR also transform like tensors. But these things called Christoffel symbols, which are important to us because they help us do calculus, they aren't tensors. And why is this important? Because we want our physics to be independent of our choice of coordinates. So that's why we're working with it. So, understanding a tensor is as much to do with the outer product as it is to do with the change of coordinates. And next time we're going to focus on change of coordinates. So to leave you today, I'm just going to talk about a few pieces of information about tensors in terms of their operation. Okay, so if you remember what I'd written out here, yeah. So from this, okay, and from this definition, if you remember the calculation I told you that was important for vectors, this thing here, right? I want you to go home and prove that you can do a similar calculation with tensors. And I want you to prove the following statements. The first statement I want you to go home and prove is that components of a tensor can be raised and lowered by the metric. That's the first thing I want you to prove, that if I have G mu nu, or if I have T mu nu, I can act upon this with eta mu nu on T mu nu. This should be equal to T. Okay. This is an exercise to prove that I can raise and lower tensor components. I was going to say that the other thing that this shows you, if you scroll up here, is that if I have contracted indices, which are dummy indices, which are A, B here, I can raise and lower them and not be worried about the consequences because they are the same. Right? They're the same. So if I write it as long as they're contracted, it doesn't matter which one is up and down, which one is mixed or not, as long as they remain contracted. That's the second property. The third property is I can see it has a linearity, which I showed you here. This is my claim that I've made. I think this is something that you should go home and prove. And then what we'd like to do next time is talk about the change of coordinates. That won't take more than 10 minutes. And if we can do that, we can finally go to connection. And if we understand connections, you're ready to do GR. You have everything that you need to solve Einstein's equations, understand black holes, understand frames of reference, and do physics in a curved space. So after this, after the next talk, I don't think there's any more mathematics that needs to be learned. Any questions today? I want a question from all of you. Like, a lot of you haven't spoken at all today, so I'm going to switch the screen off, and I think we'll just talk about what you've seen so far. Stop sharing. I'd like to hear from all of you.
Am I audible? Okay. I've got questions, but I need to organize those, and I will ask you soon, like after organizing those, because still I'm confused with certain. So,
Okay, no problem. No problem. If you have questions, write it out. All the steps that I did today, try writing it on your own and seeing if they make sense to you. Any other questions? Is Pugal still here? He's gone.
Pugal is not watching the stream. Yeah, not.
He's not in the call. Anyone else? Like, what do you think? Do you have any questions from what you've seen so far? Because this is fundamentally important to Tensor. If you understand today's talk, then you're set.
Chinmaya, I have just one question. When are you going to send us the problems?
Send you problems.
Yeah.
Yeah, I'll send you problems. And I've given you at least 5 or 6 groups to do. I can give that to you again. And yeah, I'll give you some other set of problems.
Mm-hmm. All right, sure. Look forward to that.
Any conceptual questions today?
All right, so a tensor is essentially a special kind of a map, right? In a sense.
There are multi-linear maps. There are maps that eat vectors and return real numbers. That's another exercise you can go back and do. If I have a tensor of rank 3, which you should now relate to having 3 basis vectors in its outer product. What happens if I only feed in 2 vectors into a tensor black thing? What happens? Just try plugging that into the formula, and I want you to do your research, and just from the formula, tell me what you see.
Hello.
Yeah, Makan,
Yeah.
tell me.
Okay. Yeah. So I was talking the whole time, and I like nobody could hear me. So once again, yeah. So I had a question. Like when we were doing the derivative thing, so you introduced the Kartoffel symbol there, right?
Yeah, but I haven't told you what it
Yeah.
is. I haven't derived what it is. I've just told you that be careful. Not all things with indices are tensors.
Yeah. Yeah. So based on what your definition of connectors was previously, so is Kartoffel's symbol like a connector of sorts or something?
Christoffel, not Kartoffel.
What? Oh, sorry, Christoph. Sorry. Yeah.
What was the question?
No, like the way you define connectors in this connectors, right? To
I haven't defined it yet. I said we're going to look at connections next class, but next talk. But
six.
I just said that there exist these things. I haven't spoken about it yet. So any statements can't be held against me so far. What was the question though?
No, like is the Christopher symbol a connector of sorts, connection of?
They're the same. Okay, so a connection is the Christoffel symbol. They're the same with caveats. So if you remember the definition I gave you of space-time in the first place, can anyone read out that sentence I told you? You may have it written down. Does anyone remember what I said space-time is? Can anyone read out that definition for me, please? Because I've lost it. There's a particularly good definition of space-time. Does anyone have it? It says something like space-time is a 4-dimensional topological manifold equipped with a smooth atlas. Do you remember that definition? There was one particularly important statement in that. It was to say that it has a torsion-free connection. Do you remember that? It's not. I don't expect you to remember it because it was just written out and there was a lot of jargon back then. But now, hopefully, when you read out the definition of what spacetime is, perhaps you'll understand what the manifolds are. You'll understand maybe understand what we're hinting towards with what a connection is.
Okay.
But the idea is that a connection in general. Okay, so a Christoffel symbol is not the same as a connection, but if we work in a space-time where there's no torsion, meaning we're not twisting our spaces, twisting and turning, then the Christoffel symbol is the name for a connection in this special space-time.
Okay.
So the Christoffel symbol is the connection as long as you're working in a torsion-free connection. If you're not working in a torsion-free space-time, then the connections have different names. It's just like how I said earlier, if you have a parameterization of a curve where the integral vanishes because it's 1, that particular parameter is called the affine parameter.
Yeah.
It's just the same thing. That not all
Okay.
Christoffel is just a special case.
Okay.
Any questions on tensors? Because you guys, I mean, at least from Pugal, I've been hearing like fear about tensors in general. I hope you saw today that they're not really scary. Any questions? Any observations so far? Okay. Any questions? Any other questions about what we covered today?
Just a thing, Chinmaya, maybe you could talk about this, or I don't know. Depends on your comfortable. Well, you hinted at cotangent spaces or covectors. Those guys. So we obviously know that you can go from the vector space to the covector space through the metric. But okay, so we have at least an intuitive idea of what a vector is. What would you then say a covector is?
I told you
along the same lines.
We're working with Lorentz transformations. I told you the way that I like to remember them are row vectors and column vectors. That you need something like a column vector is related to the row vector. And you need it to form that real number. You've seen for yourself in the 3 blue 1 brown video that it's a unique map to the real numbers as well. So I was trying to say that if you're learning this, the easiest intuitive picture is to say that the tangent vectors you can think of as row vectors, the cotangent you can think of as column. Like they're related to each other. You'll work with in physics, you'll find that sometimes they're one and the same. They're called self-dual. But the idea is that it's a consequence of vector spaces in general. So I was just thinking that it's I've tried to tell you this before, that often you might find, like you were asking me, like what exactly is a tensor, but I told you that the easiest way to think about a tensor is to say that, well, if you feed it two vectors, it'll give you a real number. If you feed it one vector, it gives you another vector. That's the easiest way to think about it. I was thinking that in an intuitive way to think about cotangent spaces is this way. If you'd like, I can do a little more research, because I'm particularly careful about what I say if I'm teaching you guys, because I want to make sure that I've thought about the answer to what I'm giving before I tell you. So if you'd like, I could spend a little more time thinking about how I teach cotangent spaces in a way that maybe might make more sense. Because before I talk to you guys, I work through the different examples I have to use and see if that makes sense, so that I can pick a different one. So let me just think about that, and I'll get back to you soon. Any questions in today's class? Anything else? None? Okay, so I'll upload a list of questions that are exercises. I hope you found today's session useful. I really think it's the easiest way to think about tensors. And this is something I spoke to you about earlier, that when I said vectors are things that transform like vectors, that's not what I meant. But I meant to say that in general, we can define, just like how I define the quantity in terms of an outer product, I can equivalently say a tensor is defined as something that transforms in this particular way. And I can say a vector is something that transforms in this particular way. And that thinking about quantities as how they, in terms of how they transform, is also extremely important in physics. And I was trying to say that in particle physics, you'll find that the only way you can honestly define an electron or define particles is by the way that they transform. That's the only good mathematically rigorous definition that you get. And when you go into further physics and you pursue research, you'll find that understanding how these things change under coordinate transformations is very, very fundamental. You can get non-trivial results just by thinking about the way they transform. In fact, that's also honestly how you'd find the Higgs boson as well. Like thinking about how you have a particle that gives every other particle a mass, you start by understanding its transformation. So that's something that I want all of you to think about. And it's something I'm bringing up because I don't think it's mentioned, at least in the Indian undergraduate curriculum, but it's a fundamental. Any questions today? Because if you're not asking me questions, I assume that everything that I've shown you so far you're clear with. And I walked you through a few calculations. And I think this format might have worked better given that indices may be challenging if we haven't worked through them. Okay, if there are no other questions, I think we'll call it. And if you want to discuss anything further, send me a message on WhatsApp.
Sure, yeah.
Okay, have a good day.
Thank you. You too.
All right,
Have a good day.
day.
Thank you so much.
Bye. Yeah.